Good night, everyone. Mechanics of materials. Last time we review a structure, a configuration which consists of a boom AB, rod BC, and they are like connected by pins at all supports, and then a 30 kilonewtons applied at pin B. Last time, by drawing a free body diagrams for all the structure, we calculated the internal force in each member. This time we want to calculate the normal stress, shearing stress, and bearing stresses wherever it applies. So again, we had the front view, we had like a top view and also the end view of our configuration at B, like here. So this is what we can see when the 30 kilonewton force is applied there. Definitely we have like a single shear at C and double shear at BA and B. So for calculating the normal stresses, if we know like our boom AB, like what you can see here, if you remember, there was a 40 kilonewton compression force and there is a tensile force inside the rod BC. I will provide you with that link so you can have a review of how we can get to know what these forces are. And then as soon as we know that boom AB is in compression and then rod BC is in tension and what their forces are, then we can just simply look at the structure. So for first, normal stress in boom AB. So this is our boom AB in compression force like 40 kilonewton applied at both ends. And if we closer look at that, we can get the dimension of boom AB. So this is boom AB. And then sigma or normal stress is nothing but force over the area. So the cross-sectional area is 50 times the thickness, which is 30 millimeters, and it just gives you a negative 26.7 megapascal. So sigma AB, normal stress in boom AB, is a negative 26.7 megapascal. Then if we just move on to rod BC, it just handles a 50 kilonewton tensile at both ends, and we have the diameter as well. Then sigma, normal stress at BC is positive because it's a tension. Then the forces over the area, which is pi times d square over 4 times to 10 negative 6 meters squared. And it just gives us a 159 megapascal or 10 to 6 pascal. Now we have the normal stresses in our members. Let's jump to a different section of B, rod BC. So the flat part, we are talking about this part of rod BC, almost the connection. So the flat part of the rod BC is under tension and at its narrowest section. So we need to, because there is a pin here, we need to go with the net area. So that's definitely 40 millimeters minus the diameter of the pin times the other dimension of the rod, which is like 20 millimeters. So that's the thickness. And then this is the width, which is this is our cross-sectional area for the flat part. So as soon as we have a net or net area, we can simply apply the same force over the area, and it just gives us sigma BC for the narrowest part of the section in the flat part is 167 megapascal. But just be careful, that's an average a value because definitely due to Saint Venant, the rule, the stress closer to the hole are much higher. So let's see what is that. This is an average value close to the hole. The stress will reach a much higher value, and that's due to Saint Venant's principle, which is it just says if we have like a hole inside our plate, the distribution of the stress is like this. So the more closer to the hole you are, you are experiencing much more stress. So this is the stress distribution. So this is the far end, this is the close end, and we just remember what we calculate for our case is something like a an average value. It's not the real value of sigma maximum close to the hole. Okay, let's jump to the shearing stress in connections. Let's jump to P net C, like what you can see here. So it's in a single shear, so you can easily see we have the diameter of our pin and we have like a 50 kilonewton tensile force applied at it. It's simple, it's at single shear, so simply divide the force over the area of your pin, which is pi times 25 to the, over 2, which is the radius squared, and then tau average is just force by the area. And because it's on a single shear, you just need to simply replace the area in the formula. It just give you 102 megapascal for the pin at C, which is a single shear. Now let's jump to the connection at A, which you can simply see that's a pin at A is in a double shear and a compression force of 40, a compressive force of 40 kilonewtons applied at its both ends. So if our pin is at a double shear, same a cross-sectional area, you can easily say now tau maximum is tau average is P over the force over the area. You can simply replace it a half of the force because or double the area. So either of them works. You just use two of the areas like A prime or just divide force by 2 because each of these force are 20. You can simply divide each of them. So that gives you a tau average for a double shear at A is equal to 40.7 megapascal. Now let's jump to the pin at B, which is consist of a part for boom AB, a part for rod BC, and also the bracket one. So this is like pin at B, which is consist of 5 parts, 2 for booms, a boom at AB, mm, 1 for rod BC, and 2 for brackets. So if we can simply say like see it this way, due to symmetry, just put like a 15 and 15 of these 30 kilonewtons at the edge of the pin, like what you can see at both ends. Then you just move on. And if you remember, this is like boom AB, if you remember, and it was under a 40 compression force. So the same force applied to the pin. So if we just put it like a symmetrical, a half of that applies here, half of that applied to the other half of the force. Then there was a rod BC, which handles a 50 tensile force. So the same force applied, we can put it here. And that just goes by half of the structure due to symmetry. So it just says if you look at it from the side, there is a half of Q which is 15, then you move to half of FAB, and you can also consider this force which is 50, half of that apply to G, and the other part is applied to H due to symmetry. So if that's the case, we can like keep a closer look at pin B. Due to symmetry, we just divided like by half. At the very edge of the pin, that's a half of Q, which is 15 kilonewton. As you move to the right, there is a half of FAB, that's 20, because the total force of AB is a 40. And then if you just put this force like a half of that over G, half of that at H, that's 25. So if you do so, you can easily see, you can put it like this. Then due to symmetry, PG is like PH is equal to 25 Newton. So then for all of these forces, you can easily see the maximum value between 20, 15, and 25 is 25. We get this number to calculate our a tau average to be in a safe part. So tau average at B is equal to 25 over the area of the pin. And if you do so, it just gives you a positive 50.9 megapascal. So again, how we got that? We just consider a joint at B like a symmetrical part, then a half of 30 kilonewton goes at the each ends, then half of the force of boom AB is just distributed each of, and then FBC is also divided to G and H by the a equal amount. So that's how we get it like a 25, 25. Then we use that 25 because that's the maximum in order to be the safe side divided by the area of the pin to get the largest shear is GNH, and we just use that for tau average to be in a safe zone. And then so far we calculated the normal stresses, shear stresses at pins, normal stress at members, shear at connections. Now let's jump to the bearing stress in boom AB. So boom AB is at compression by 40, then and it's in a double shear. If this is boom AB, you can easily see the sigma or bearing stress is nothing but the force over the area. So this is the area of our boom, which is you can see the 30 millimeters from the top, and this is the side one. So it just gives us 26.7 megapascal. And because that's a compression, definitely that's a negative one. And like bearing in boom AB, but that was for the length. But at the connection, you need to consider the pin. If you remember, for bearing stresses, when we have like a bolt and we have like a plate here, so this is the diameter of the bolt which goes to the plate, and then use the thickness of the plate. Do the same rule for our case, like at close to the edge. So our diameter is 25. So if you want to calculate this sigma at bearing stress, it's just the force which applies, which is 40 kilonewton, then over 30, because this is our, if this is our thickness, if this is our thickness like here, which is 30, so the pin, it moves just to this 30 millimeters, and then the diameter of the bolt itself is 25. So sigma bearing at the connection here is just a 53.3 megapascal. Mhm. But that's only bearing stress in the boom at the connection. But how about the bearing stress in the bracket itself? So what about this part? We just consider that for the boom, this one, boom AB. Now let's go to the the bracket one. So if you look at the bracket, so you can easily see for bracket there is the same force, but the cross-sectional area for bearing stress is different, is like 50, mhm, which is this thickness and this thickness, which just pins moved inside them, then diameter of the bolt, which is 25. So 25, 25 for each of this part. If you can see it, like this is 25 plus 25, which pins are at them, and then the diameter of the pin itself is 25. So it just simply gives us a sigma bearing stress at the bracket is 32 megapascal. Uh, Thank you everyone for following us. We calculated the forces in previous video, and in this video we calculate the normal stresses in members, then the shearing at the pins, shearing stress at pin, then the bearing stress at the brackets, and also members. Thank you. See you in next video.